that show up a lot. They are very but way too long on this problem in first period. I don't want to spend that long on it. There are two classic questions that you have to be prepared to deal with. The first is one I showed you yesterday, the roller coaster problem. The idea that there is a speed that you have to maintain at the top of the roller coaster, or the roller coaster car will fall away from the track. Do you guys remember that yesterday, right at the closing moments of the class? If the car is going too fast, that's fine, because it's just going to press up against the track and the track will curve the path. But if it's going too slow, it falls away from the track. The radius gets smaller than the radius of curvature of the track, and it becomes a projectile instead. So we want to find out, how fast do you have to be traveling in order for the cars to stay against the track? Now, I want to be really clear. Once you've done this once, it's the same answer every time. But students have a really hard time with the whole point. And I try to make this as easy as possible. First, I'll remind you that there are only two possible forces acting on the object: its weight and normal force. This is something that students just don't seem to want to put together, but the only way you travel in a circle is if your forces are unbalanced. This clearly looks unbalanced. That shouldn't be a problem. But again, the only way you travel in a circle is if your forces are unbalanced. So because of that, these are the two forces. I make them both positive. That's the other thing you put in your notes. When dealing with the centripetal motion problem, the direction to the center is the positive direction. So make them both positive and set that equal to MAC. This is our unbalanced force, and that causes centripetal acceleration. Now, the cars have to have enough velocity for this ratio to work. And here's where, I don't know, maybe it's just me. Maybe I just can't explain it right. I'm putting the V and the N in blue on purpose there, because once the cars are traveling in the roller coaster, the thing that determines whether you're going to be able to make this turn isn't your weight, right? You need to be going fast enough. And if you go faster, this side of the equation gets bigger. Everybody agree? Now, the other side of the equation has to equal this. So this can't change. So if you go faster, that doesn't mean the weight is going to get bigger. But if you go faster, the track could press on you more. Does that make sense? Oh. Faculty meeting this morning. Back to work. So, as I was saying, if you go faster, N can get bigger. So if you make the roller coaster car go faster, you just get the track to press harder on the car. But if you go slower, N has a smallest value. The smallest N can ever be is 0. Right? The normal force can't pull up on the car like the marble. Just can't do it. And should that happen to your roller coaster, bad things are happening if they have to use the safety mechanism of the roller coaster. So there is a minimum speed. You need to go faster than that, because the track can push on the cars down. That's fine. But you can't go slower than that. And the minimum is when N goes to 0. Now, yeah, you can figure out what this is. In fact, this is a boundary condition. This condition must be met for the car to safely make it through the roller coaster. I'm saying that because what if the question was asking how high on the track do you have to start the cars? Now, that's a problem at this point you should be able to do. But you have to know this first. You have to do the force part of this problem first, because that tells you how fast the cars must be traveling. Then you could do the energy part of this problem, because this is also an energy problem where there's gravitational potential energy here, and there's kinetic and gravitational potential energy here. This problem we talked about last week, I'm just adding the circular problem to it. Everybody follow okay? Because I'm going to change it now, problem. And this one is just, it's the same kind of question, but students still have a difficult time wrapping their mind around it. What if you make a portion of your problem where there's a roadway that's circular, but you're going to travel over the top of it? So if the car has a velocity this way, can you draw a free body diagram for the forces acting on the car here? You're going to make a mistake unless you've really been paying attention to me. And not about all the security stuff, but about, physics. So please draw your 2 arrows. You have to draw 2 arrows right now. Free body diagram. There's normal force and weight. And I think you're going to screw this up. Not because you're not smart, but because you're not thinking. Does the roadway look like a circular path? Does the roadway look circular where the car is right now? I'm talking about right here. Does that look like a circle? Well, I want it to look like a circle. I put a little indicator that it has a radius of curvature. So it's a portion of a circle. I'm bringing that up because in order for the car to travel on that path, the net force has to be unbalanced so that there's a centripetal acceleration for the car to go over the top of the circle. Now, that can only happen if the forces themselves are unbalanced. So when you drew the forces, did you draw weight downwards? And were you careful to recognize that the only other force acting is normal, and that the normal force will have to be smaller than the weight? Because they have to be unbalanced, or else the object doesn't travel in a circular path. It's not like the weight can get bigger all of a sudden, but the normal force can get smaller. Now I'm bringing this up because it looks to me like we have weight downwards towards the center minus normal force upwards away from the center. Remember, the positive direction is towards the center of the circle. And if you haven't written that down, what are you waiting for? I would write that down, that the positive direction is towards the center of the circle. And that has to equal mv squared over r. Again, we have this relationship between velocity and normal force. It comes down to a simple idea here. If you go faster, then it's going to take more force downwards to get you to curve your path along the circle. So I need to subtract less normal force if you want to go faster. I mean, if you stop, the normal force will just be equal to the weight. It doesn't have to be unbalanced. But the moment you start moving, the normal force becomes less. What that means is you could go fast enough for the normal force to go to 0. That's the moment where you are no longer in contact with the ground and you are not traveling in a circle. You have turned yourself into a projectile. The ground will curve away out of the way underneath you, and your radius will be bigger now, and you are a projectile. That's the conditions for a jump. So if you go over a small hill fast enough, you can reduce the normal force to 0. That suggests that there is some maximum speed. And that maximum occurs in this case as the normal force goes to 0. It's a similar problem to what we just did. But again, this is the maximum. You need to stay at a speed less than this if you want to stay in contact with the ground. And still, I'm pretty sure we could turn this into an energy problem if we really wanted to. I see an energy problem here, but to understand the energy problem is to understand that the force problem has to be done first. This is the condition. This decides everything else about the problem. So we can go slower than this. We can't go faster than this, or else the car leaves the track. Now, these kinds of conditional problems are tough. I don't think we're going to see these on multiple choice, like your semester exam. I do believe you will see these kinds of things on the AP exam. So we'll practice more of this next semester. I'm not going to dwell on it now because I don't think we have to worry about it next week. I think we have to worry about something else, and that is gravity. We're going to talk about gravity and orbits. Gravity is brought up in this chapter because orbits are circular. So an orbit is simple. It is the balance between gravity and velocity. We'll get to that more tomorrow than today. Today I want to talk about gravity. Up to this point, we have said that gravity is mg. That's not true. That was a shortcut that worked while we were, trying to learn about weight and forces and such. The real force of gravity is a little bit different. And you might even remember the definition that I gave you way back in November or October. That the force of gravity is the force of attraction between any two objects with mass. That's what I said way back in October. The force of attraction between any two objects with mass. So there's a attractive force between me and my coffee. And that attractive force occurs because me and my coffee both have mass. Now, this is true about any two objects in the universe. You and the person sitting next to you, your backpack and your water bottle. Every two objects is experiencing a force, which means you are experiencing multiple forces of gravity in all sorts of directions, because all objects with mass are acting on you. Now, the force of gravity is a very small force. It takes a lot of mass in order for you to experience the force of gravity. But the force of gravity as an equation is a little more complicated than what we've been talking about. This is the actual gravitational equation, Newton's law of universal gravitation. I don't know how Newton came up with this one, to be honest with you. This says that if you have two objects, mass 1 and mass 2, and they are separated by a distance r, the force of gravity between them will be the product of their masses divided by the separation distance squared times a constant. Now, this constant isn't the acceleration of gravity. This is not 9.8. This is uppercase G and has a name. It's called the universal gravitational constant. Bless you. Well, if you're going to move mucus, you should go ahead and make it aggressive. I think it's the way to go. I hate those dainty sneezes. Those are just dumb. I like a solid sneeze. I hate those people who just like twitch and that's their sneeze. It's terrible. I mean, you totally like, you can have a sneeze, enjoy it. Ride that sneeze. Lean into it some. Move some things around. Reorganize. That's what a sneeze is supposed to do. I mean, I hate the dainty sneeze. The dainty sneeze makes me crazy. I actually have a student a couple years ago whose sneeze was achoo. They would go achoo. I'm like, you've got to be lying. She goes, no. And you know what happened as a kid? She trained herself to do that. You don't do that naturally. Watch baby sneeze. They love it. They get all the way in. They commit because they don't know what's happening to their body. It's like a full body activity. Baby sneezes are awesome, and they just blow stuff everywhere. They have no desire to hold that mucus in. It's awesome, especially if it's not you. There's that baby at the other table while they're eating. Yeah, I love watching other people with their babies. Young parents who have no idea what they're doing. Oh, those are good times. Good times. Yeah. So yeah, when you're gonna sneeze, just go ahead and let it out. That's all I gotta say. All right. So the universal gravitational constant It is super small, 6.67 times 10 to the negative 11th. This is why you don't really experience the force of gravity between you and other objects. Because no matter how big your mass is, you have to scale it by this. And 10 to the negative 11th is really small. Now, there's weird units here, and you do have to know these units. It's newtons meter squared per kilogram squared. Because you have this equation, and it has to be left in newtons when you're done. So the gravitational constant has some weird units. Now, to understand how this works, you need to know that there's 3 different ways they're going to test you on this. The first is they're going to make you calculate the force of gravity. That's obvious. You can plug some numbers in there and get your answer. We're going to try that in just a minute. The most likely way they're going to test you on it, though, has nothing to do with this equation. It has to do with your ability to deal with ratios. And so far, students have proven generally that they're pretty bad at ratios. So I want you to understand that this is the actual force of gravity equation. I'm going to prove that to you here in just a minute, but it will involve your calculator if you want to see it proved to you. So if you have your calculator, please take it out, and you'll is 70 kilograms. So I want to use the Earth here. So here's the Earth, and here's you. And we're going to talk about the force of gravity between you and the Earth. The Earth is big. And I'm not sure you guys have an appreciation for how big, but the Earth has a radius of 6.37 times 10 to the 6th meters. That's the radius of the Earth. And when I say big, I mean big. 5.96 times 10 to the 24th kilograms is the mass of the Earth. So if you're going to calculate the force of gravity between you and the Earth, remember, this is the force that acts on you. There's also the force that acts on the Earth. Then I've given you everything you need to get the value for the force between you. This is actually how you're supposed to calculate your weight. Mass of the Earth, mass of you, times g divided by the radius of the Earth squared. So if you would please take a moment and calculate the force of gravity on you. You are practicing with your big numbers. I'm going to give you a hint because most people screw this up. Multiply the top numbers together first and write that down, and then square the bottom number and write that down, and then divide them. It'll give you the least number of mistakes here. We're not going to do this, Kyle. Why was it out of your backpack? You need to calculate something in your car? That's very unlikely, Kyle. No, okay. No. I don't need an explanation. Whether what you're getting is the right answer or not. You're getting to some number. And most of you don't know what your weight is. Do you have a question? Then you're not doing it right. But I will tell you that the first number would be 5.96. Then you would hit second, comma, 24, and then the times. But I'm not going around to show people how to use their calculator. Well, you have to work it out. You don't use the minus, use the negative. But like I said, I don't show people how to use their calculators. I will during tutoring time. Now, look, we're not going to spend a lot of time with you pushing your buttons. You need to do that so you can figure out what you're doing. But again, I can't possibly wait for everybody to push their buttons. We don't have that kind of time. But here's how we're going to figure out whether you did it right or not. If this is the only force acting on you, that has to equal MA. Right? Has to. So if instead of you standing on the Earth, you are falling towards the Earth, then we could find out what this acceleration should be by taking that number, whatever it is, and dividing by what you used for your mass. This should give you the acceleration you are experiencing due to the force of the Earth, which should be 9.8. You'll know if you've gotten this right if when you divide that number by your mass, you get 9.79. That's how you know you've done it right. Has to work out to be your weight. Now, if you're not getting that, I am not going to spend time helping you figure it out. You need to figure it out. You need to work on your calculator and make it work. This is very unlikely to be the kind of multiple choice question they're going to ask. It is, however, the kind of problem you might have to have in the FRQs. So when it comes to punching the buttons, work out your problems. But folks, we're going to move on because this is not that interesting. Arithmetic doesn't interest me, and it shouldn't interest you. So check your math, work it out. What I'd prefer to show up, the first one is this one. Two objects are placed a distance r apart. They experience a force due to gravity of 20 newtons. If the distance is doubled, what is the force of gravity that they experience now? I'll say it again, but only one more time. Two objects are placed a distance r apart. The distance between them is doubled. What is the new force of attraction that they experience? These are ratio problems. I don't know whether you are good or bad at doing ratio problems. I'm going to give you a set of steps to do a problem like this. These problems generally all are the same in that they're going to give you a parameter, they're going to change a parameter, and they're going to ask for what the new value is. So the first thing you have to identify is what relationship are they trying to get you to use. That should be easy for us. The relationship we're trying to get us to use is the one I just introduced. So that part's easy. The second thing you're going to do is put in the values as given and what they equal. So for us, we don't really have any values, but we know that they equal 20. So I'm going to say 20 equals m1 m2 g over r squared. That's step one. Step two, put in the new values as given. So I'm going to put in the new values as given. That's going to be m1, it didn't change, m2, it didn't change, g, it didn't change, r was doubled. Put in new values as given. Okay? Now, this next part is not hard, but pay attention. Separate the numbers from the letters. So I'm going to pull the letters to the left and the numbers to the right. I'm sorry. I'm going to pull the numbers to the left and the letters to the right. That's what I'm going to do. So on the top, there's no number. So I'm going to pull a 1 and have M1, M2, G. In the denominator, I have a 2 squared. So I'm going to pull the 2 squared out. I'm going to leave the r squared here. What you get for the letters should be what you got when you started. The letters should equal what you had at the beginning. So I will replace the letters with the value we had at the start. 20. And now the answer is 20 divided by 4, or 5 newtons. The new force is 5 newtons. This is a ratio problem. This is one method to do ratio problems. There are others. If you don't like this method after you practice it a couple times, I will give you another method. I'm going to give you some practice tonight. It's going to have this kind of stuff in it. Practice it. It won't take you long. If you don't like this method, say, I didn't like that method. Do you have another one? I do. This is the one I'm teaching this year. Seems to be pretty effective. We're going to take a look at another version of this, okay? So we'll do another practice. I don't know if you paid very close attention a minute ago, but we found the acceleration of gravity when we were talking about the force of gravity on you. Did you realize what we did? We took the mass of the planet, the mass of you, g, divided by the radius of the planet squared, and set that equal to the mass of u times a. That's what we did when we were first using this. And we can cancel out the mass of u, leaving you with the acceleration of gravity looks like this. It's not a new formula. You're just setting the force of gravity equal to ma. This is the acceleration. Now, this actually would give you the acceleration on any planet. You would have to know the mass of the planet and the radius of the planet. So how might they want to use that on your exam? It's like this. You travel to a planet that is twice the mass, but 3 times the radius of the Earth. What will the acceleration of gravity be on that planet? You travel to a planet that has twice the mass, but 3 times the radius of the Earth. What will the acceleration of gravity be on that planet? So here's how you do that. Step 1, put in what you know. They're comparing this to the Earth. We know the acceleration of gravity on the Earth is equal to 9.8. I'll make sure she gets it. I said thank you, right? Tried to use my manners. Now, this is what we know. Second step, put in the ratios that we were given. Put in what changed. Our new planet has twice the mass of the Earth and 3 times the radius of the Earth. So we are putting in the ratio, we're putting in the things that changed, that were compared to the Earth. Now, separate the numbers from the letters. So I'm going to pull the numbers to the left and the letters to the right. I'll get 2 times MEG divided by 9 times RE squared. Right, when I pull the 3 out, I have to square it. Next, we will have something that we can use for the letters, 9.8. So this has to equal 2/9 times 9.8. Our new planet is going to have 2/9 the gravity of the Earth. So even though it's bigger, gravity's less, a lot less. Now, a lot of this stuff has nothing to do with physics. They exploit equations that have exponents. They could do the same thing about kinetic energy. They could say 2 objects are moving, one has twice the velocity. How do their kinetic energies compare? They're going to use equations where there's an exponent. That's all they do. They're not really physics questions. But these 2 questions get this kind of stuff all the time. You guys can see that too, right?
Yeah. I thought it was the fire alarm.
Trying to exaggerate the part of the equation that has the greatest impact on deciding the size of the thing you're measuring. So for kinetic energy, if I want to make something have a lot more energy, I change its velocity. Because small changes in velocity have a bigger impact on the kinetic energy. Same when it comes to gravity. If I want to have a big change on gravity, I change how far apart the objects are. That has the bigger impact on the size of gravity. They exploit that for the questions on the test. That's what they're going to try and do. And since all the equations we have so far have just been mostly linear, the only time we have things where there's a square is those two and one more, the spring. That's the only ones that they really have where they can exploit that exponent. So it's always one of these three. There's probably going to be something on the AP, on your semester exam. It's going to be one of these three things, and they're going to do a ratio like this. Yeah.
Are we going to go over like what part of the semester we're going to have?
Not today. But and I can't say anything like this out loud. What I will say is tomorrow I might mention page numbers and other numbers. I have no idea what they will mean. But if I say a string of numbers tomorrow, you might want to, I don't know, highlight something. Okay? Now, we do not have time to really do what I wanted to talk about today. However, we have time to get started. The reason why gravity is always associated with circular motion is because of orbits. Orbit is the final topic of the year. And we're only going to talk about circular orbits. But a circular orbit is a perfect centripetal motion problem. It's a perfect centripetal motion problem. And the reason I think is obvious. An object that is in orbit is experiencing a single unbalanced force towards the center of the planet. All right.